Welcome to ImageGrafix webinar. Today's topic is overview of Flange design and some key new features of PVLE 2019. So this is your first slide where we have shown various type of flanges used in the industry. So if you see over here, the first is your well neck flange, okay, and the second and third is your full face flange. The fourth one is your slip-on raised face. Fifth and sixth is the tongue and groove, like so and so tongue and groove will be there. Seventh one is the RTJ type. And the last one is for your all-round cross section. So the flange is called as a all-round flange and the all-round cover. Okay, so these are typical flanges which are used in the industries. Then these are various type of gaskets mainly used to seal the flanges. So the first is your ring type, RTJ type metal gasket ring, and the second is your raised face where you use it as a O, and the other below one is your full face gasket. On the right hand side it is a rubber gasket, raised face as well as full face. So for full face it will go through bolt and the gasket ID and OD will be similar to that of your flange ID and OD. Okay. Then O-ring gaskets are there on the leftmost bottom corner. Then there is a spiral wound gasket. In case of your spiral wound gasket, like it is having inner ring from inside and the outer ring from outside. So what is the purpose of inner? The inner ring is basically used for the protection of that gasket from temperature as well as from the pressure. The outer ring is basically for the centering purpose, to center the gasket with reference to the bolt hole and with reference to the bolt. So your gasket surface will be having higher thickness in case of inner and outer ring. And this is the surface under pressure it is going to compress, and hence the leakage will be avoided. Okay. The second last one is your cam profile type of a gasket. This is again a metallic gasket with filler in between. And the last one is the gasket which we basically use for heat exchangers for the passes. So these are the various type of gaskets generally used. So as far as your non-standard flange is concerned, the mandatory appendix 2 is dedicated for the non-standard flange design. So whether all those type of flanges what we have seen in the first slide, okay, whether these can be designed with the help of appendix 2. So the answer is no. So not every flange can be designed whatever we have seen over here. Okay. So there are some flanges which cannot be designed in appendix 2. So let's understand the scope of mandatory appendix 2. So the scope says that the rules apply specifically to the design of bolted flange connection with the gaskets that are entirely within the circle enclosed by the bolt holes and with no contact outside this circle. So what does it mean? Your gasket has to be inside your bolt PCD. So there should not be any portion of your gasket that should extend beyond the bolt circle diameter. Okay, so this is the first limitation on the basis of which your appendix 2 flanges are designed. So no full face gasket can be designed with the help of these type of flanges. But as we know, PVL it does this. So how it is doing it? So PVL it does with the help of Tailor Forge bulletin. Okay. Then NR to be used in conjunction with the applicable requirements in subsection A, B and C of this division. Okay. Then when we have seen the last flange in the first slide, which was non-circular in nature, okay, that was an all-round flange. So can we design all-round flange? So there is a subsection 2-10 which is dedicated basically for the non-circular cross-sectional flanges. So there they had given one analogy that is applicable for the non-circular flanges. but the bore of those flanges needs to be circular. So if the bore is also oblong or some elliptical in shape, then these rules are not applicable. Okay, so non-circular flanges with non-circular cross section cannot be designed as per mandatory appendix 2. So what we have to do, so for that we have to go to U2G, and as per U2G we have to design the flange with some other references or some codes or methods which should be as safe as the design of this division, and that should also be acceptable to the AI. Okay, so that we have to take care on that. So now we are seeing the two different type of flanges over here, out of which the left one, which is having the circular bore, can be designed with the help of appendix 2, and the right one cannot be designed with the help of appendix 2. So we have discussed on this why we cannot design. Okay, then another thing is listed over here is we can use the standard listed flanges as mentioned in UG 44. So whatever your standard flanges of B16.5 and 47 are mentioned in UG 44, it can be directly used without any calculation as per the pressure temperature rating provided in that respective standard. Okay, then one can use the other type of flanges other than the flanges which are covered in mandatory appendix 2, but those should be designed in accordance with good engineering practices, and the method of the design should be acceptable to the inspector. So what are these other type of flanges? So the flange covers as shown in figure 1-6. So when we are going to see 1-6, it is nothing but disc end along with the flange. Okay, so disc end is an integral part of that flange. So those constructions are not directly covered in appendix 2. So these type of flanges also can be used if it is required. Okay. Then the next is the bolted flanges using the full face gasket. Okay. Now if there is some full face gasket, then those type of flanges also cannot be designed as per appendix 2. So these flanges will be designed as per either Taylor Forge bulletin or some other references, and the code like PD 5500 does cover the full face type of a flange design. Okay. Then the next is flanges using the means other than the bolting to restrain the flange assembly against the pressure. So there are certain applications where your quick opening type of the flange are used, where the opening or the tightening component is like a C-clamp type of a structure which will be sitting on the top of your flange where your gasket is actually located, and then with the help of the nut you will be applying pressure on that. So these type of the restraint type of flanges are also can be used basically in the ASME vessels, but as we all know, the design procedure is not provided in appendix 2. Okay, so mostly you will find this in basically in the pharma vessels. Okay, so so now this figure 1-6, what we were discussing just now, these are those type of the flanges with the disc end. So here the disc end is directly connected to the flange. The SF or the skirt of that disc end is directly inserted in the flange and it is welded with the flange. So there is no other component over here. So the disc end is directly attached to the flange. And the other is the full face gasketed flange. So whether PVL does the full face type of the design? So the answer is yes. PVL does this as per Taylor Forge bulletin. Okay. Now some other more important considerations whenever we are designing the appendix 2 flanges. So first point over here is when the flanges made from the ferritic steel shall be fully annealed, normalized and tempered, or quenched and tempered. This type covers those design in which the flange has no direct connection to the nozzle or the pipe wall. So these are basically used as a LJFF, that is the lap joint fat face flange, where there is no direct contact or attachment between the flange and the shell nozzle or the wall. So these type are also called as a loose type of flange, but some other type in the design where the method of attachment is not considered to give the mechanical strength equivalent to the integral attachment. So this is the definition given in the code for the loose type of flanges. So there are figures which are given in appendix 2. So figure numbers are 1, 1a, 2, 2a, 3, 3a, 4, 4a and 4c. Okay. So let's observe the figure. So these are typically used as a loose ring flange. So if you observe the joint, the figure 1 and 1a, these are loose flanges. Okay. So if you see in the first figure, the vessel wall or the nozzle wall is integrated as a stub end, and the loose ring flange is not attached with any kind of a welding with this stub. So it is free to move on the surface. So this is called as a loose ring type of a flange. Now if we go to the second figure, that is 1a, it is also not welded with the shell, but only the change with reference to the first figure is that the stub end is not integral part, okay, or the forged part of that nozzle. So it is actually fabricated and directly welded to the nozzle. So that's why the outside there is one fillet, and the flange should also give some relieving chamfer so that it should not interfere with your outer fillet when the flange joint is going to be tightened. Okay. Now if you observe the figure number 2, it is basically the joint between your flange and the nozzle wall or the shell wall is just a fillet joint. So if you observe all these type of welding, these are just fillet joint. There is no bevel or cut provided in the flange, and hence these joints are considered as weak joint. Okay. And also we cannot consider the strength of the shell as contributing to the strength of the flange, and hence we are considering these flanges are loose ring type of flanges. So what you see over here, there is no bevel or the cut in the flange provided. Now the other type is integral. So as the name suggests, it is an integral. Means what? So it can be from the same forging or casting where your nozzle neck and the flange are forming a single unit. So that is an integral construction. So these are basically used for the higher strength or the higher pressure kind of an application. But as the name suggests, it is not always an integral part. So there are some joints or the welding configuration which are also mentioned in this standard. So if we adopt to those, then the shell also can contribute to the strength of the flange, and hence we can consider both as an integral construction, and hence it is also called as an integral type of a flanges. Okay. So in terms of code, how they have written is this type covers the design where the flange is cast or forged integrally with the nozzle neck, vessel or the pipe wall, but welded thereto or attached by other forms of arc or gas welding of such a nature that flange and nozzle neck, vessel or pipe wall is considered to be the equivalent of an integral structure. Means what? If the flange is welded by some construction to the vessel wall or the nozzle wall, the weld joint is having enough strength so that the nozzle and the shell wall will behave like an integral element, and hence we can take the advantage of the strength provided by the shell or the nozzle wall to the flange design. Okay. So these are the figures, typical figure you will find it 5, 6, 6A, 6B and 7, which are used generally as an integral type of flanges. So here the figures are. So if you observe the first figure, which is nothing but your figure number 5, so the flange is an integral part of that vessel. So this is also called as integral. Now if we observe the figure number 6, it is a weld neck flange, okay, where if you observe there is a butt welding between the dish stand and the nozzle. Okay. Then figure 6A and 6B are also nothing but there is a butt weld joint. So if you observe the figure number 7, though there is no butt weld joint between the nozzle wall and the flange thickness, but the flange thickness will be a full penetration welded to the shell. Okay. So full welding is done throughout the thickness of the flange, and there is an outward fillet also. So these kind of construction are considered as integral type of flanges. Then the next is the optional type of flange. So What is the definition written over here? This type covers the design where the attachment of the flange to the nozzle neck, vessel or a pipe valve is such that the assembly is considered to behave like a single unit which shall be calculated as an integral flange. So by definition, optional flange is nothing but a flange which can be considered as an integral flange. But for the simplicity of the design, the designer can consider this as an optional flange, as a loose ring type of a flange, provided the following conditions should be met. Okay, so GO is the small end hub thickness where whose value is less than 16 mm. B by G0, B is your flange ID. That ratio is equal to 300. Pressure is 2 megapascal and the operating temperature is below 370 degrees centigrade. So then we can consider this construction as a loose ring type of a flange, and hence we can design this as a loose ring type of flanges. So again there are figures like 8, 8A, 9, 9A, 10, 10A and 11 for that typical optional type of flanges. So let's see those figures. So if we observe, these are similar to that of the loose ring type of a flanges. All the constructions are quite similar. Okay, but only difference is, if we properly see over here, the outer joint between the flange and the nozzle is not just a fillet, but there is a bevel in the nozzle wall or the flange wall, and hence this construction can be considered as more strengthful as compared to the earlier construction of the fillet joint, and hence we can say this type of flange can be considered as an optional type of flanges. Okay, so these are typically various type of flanges which are mentioned in appendix 2. So as the today's agenda is dedicated basically to understand the procedure of the design of flange as a non-standard flange with reference to appendix 2, where the actual pressure, actual temperature will be faced by the flange, and the flange should be having enough strength to withstand the stresses generated because of the applied pressure, and also it should have enough rigidity so that it should not have any kind of deformation from where the leakage can start. Okay, so basically the primary function of the flange is to serve for this purpose as an operating condition. So what is the definition over here? The conditions required to resist the hydrostatic end force of the design pressure tending to part the joint and to maintain on the gasket or joint contact surface sufficiently compression to assure a tight joint all at the design temperature. So this operating condition should be sufficient, so that one thing is that the pressure, the primary function of the pressure is to open the flange, and the primary function of the flange is to resist that pressure and do not have any kind of deformation, so that pressure will not leak or the gas or the liquid will not leak. Okay, so it has to sustain that pressure, and at the same time it also have to compress the gasket, so that the gasket should be properly compressed and there won't be any kind of leakage from the gasket. So these two conditions needs to be satisfied in your operating condition. Okay, as for a gasket, like there are two factors. One is called as your M factor and the other is called as your Y factor. The M factor is nothing but your maintenance factor, and Y is nothing but your gasket seating stress factor. So for every gasket, this M factor, due to the virtue of the property of the gasket, whenever the gasket is initially compressed during its gasket sitting condition, and when actually the pressure is given to that vessel or the equipment, so the tendency of that gasket is to relieve some kind of compression. Okay, so for example, let's say the gasket is having 10 mm of thickness. Okay, and after gasket sitting condition, it has been compressed to the value of 6 mm. But as the pressure inside that vessel is trying to build up, then the gasket is relieved a bit and it will be having a new compression, or it will be relieved to the value of 8 mm. Okay, so only 2 mm compression is there. So being a designer, we needs to take care of such things. Okay, so for that factor, M factor comes into the picture. So it is nothing but it is a multiplication factor used to multiply the value of the joint contact surface compression load. Okay, so that your gasket will be still under the compression even after the application of the pressure, and the load has been increased with the help of the M factor. So as we know, for various gaskets, these M factor are having various values. Like for the self-energizing gasket, the M factor is having a value of 0. For non-asbestos compressed fiber gasket, it is having a value of 2. For a higher strength gasket like your spiral wound gasket, it is having the M factor as 3. So what we are doing over here is we are increasing the joint contact surface compression load by 3 times, and hence in a way we are trying to increase the moment, load and the thickness, so that your flange should be able to sustain all these type of loadings. Okay, so this was all about the operating condition. The next condition is the gasket sitting condition. So every gasket has its own property or the factor which is called as your Y factor, which is known as the gasket seating stress. So the gasket, to avoid the leakage, it must be compressed. Okay, so depending upon the material of the gasket, the Y factor is going to change. So at the ambient condition, whenever there is no pressure, no temperature, your initial preload or the bolt load should be provided to the gasket, so that your gasket should not leak whenever any pressure is trying to build up in the pressure vessel. So this is your gasket sitting condition. So basically these Y factors are different for different types of gasket. So let's say a non-asbestos compressed fiber type of your NEFEF type gasket, it is having the value of 11 megapascal. For your spiral wound gasket, it is having the higher values compared to NEFEF gaskets. So it is having around 69 megapascal as your seating stress. So the flange has to sustain for both the condition, your operating condition as well as your gasket sitting condition at the lower pressure, where pressure is not going to control the design. Okay, so there are chances that your gasket is controlling the design of your flange, and your flange thickness is governed by the type of gasket you are going to use. So special precautions needs to be taken at the time of placing the gasket. Whenever you are designing a very low pressure or a 5 to 6 bar or let's say 10 bar pressure, so where your gasket is having very high M and Y factor values. Okay, so those things we have to take care. So the primary function of any design is to calculate the stresses. So actual stresses developed in your flange because of this gasket sitting condition and because of your operating condition. And we have to make sure that these developed stresses should be less than the allowable stress of your material, so that the flange will not going to leak because of your stresses, or it should not be overstressed because of your stresses, and the flange may fail. So the primary function is basically to calculate the stresses. Okay, so now let's discuss about the steps which are there in the code as well. So these are the various steps at the time of calculation of your flange design. So now the first step is to calculate the required bolt load. Now for operating and gasket sitting condition, we are going to calculate the bolt load. So first is the for the operating condition, okay, which is nothing but your WM1. So WM1, the formula it is H plus HP, okay, where H is your total hydrostatic end force and HP is the total joint contact surface compression load. So if you observe the formula over here, H is nothing but the total hydrostatic end force applied at the gasket load reaction, where your gasket mean diameter or the average diameter of the gasket is considered as G. The formula is pi by 4 G square into P plus the joint contact surface compression load. So the gasket will be having two sides. So the compression load will be coming on both the side of your gasket, and it is to be faced by the effective width of the gasket. So the area would be pi d multiplied by b, and we have to multiply that area with the pressure. So that's why pi into g into b will be the area multiplied by the pressure, and it will be having two sides. So that's why 2 is used as a multiplier. So 2b multiplied by pi g mp is the formula. Okay. And if you remember, M factor is nothing but your maintenance factor by which we are increasing this joint contact surface compression load. so that even after relaxation of your gasket, there will be enough compression load on that gasket so that it will not leak. Clear? So from the code, these are some of the extract, like how to calculate G, what is B0. B0 is the basic gasket with N is nothing but the nubbin length. So if you observe for various type of application, we have the basic value of B0 which will depend upon your N. And from B0, we will be calculating B. So this was all for your operating condition, okay? Now the other condition, which is your gasket seating condition. So for which we are going to calculate the bolt load as WM2. Okay. So now the load is nothing but the stress multiplied by the area, or we can put it in another way as the stress developed because of that bolt load. So WM2 divided by the area. So as we are calculating here the bolt load, which will be multiplied by the seating stress with the area. Okay. So now the area of that gasket would be pi g, okay, multiplied by the width, that is pi g into b. So pi g into b into y will give us the gasket seating bolt load, okay. So as we have calculated Wm1 and Wm2, now for this type of bolt load, what would be the bolt area required? How many number of bolts are required to sustain this kind of loads? So now we are going to calculate the bolt area. Okay. So now the total required cross-sectional bolt are AM, which is nothing but the minimum of AM, maximum of AM1 and AM2. Whereas your AM1 is nothing but the required bolt area for the operating condition. And AM2 is nothing but the required bolt area for the gasket seating condition. So as AM1 is to be calculated for the operating condition, so what we are going to do is we have to take the bolt load as the WM1 divided by the allowable stress of that bolt at the operating condition, that will be your SB, and AM2 as WM2, that is for the gasket seating condition, divided by SA, that is your allowable stress of the bolt at the ambient condition. As we know, at the start of your flange tightening, the flange will be tightened at the ambient condition for your gasket seating condition. Okay. So where WM1 is the required bolt load for the operating condition, WM2 is the required bolt load for the gasket seating condition, SA is the allowable bolt stress at the atmospheric temperature, and SB is the allowable bolt stress at the design temperature. Okay. So now as we have calculated the bolt area, now what is the total required bolt area? So from that, what we are going to do is we have to calculate how many number of bolts are required. So for every bolt, there is a root area which is available from the TEMA table D5. Okay. So from there, we will be calculating, or we will be considering what will be a root area. So what we are going to do is first we have to select the bolt. Like for example, let's say for certain size M20, there is a fixed bolt area available. We have total bolt area, then if we divide the total bolt area with the single bolt area, then we will get the exact number of bolts required. So we will be having the bolts in the multiple of 4. So let's say for example 21 bolts are required. So we are considering those as 24 number of bolts. So from this we will be calculating the total number of bolts. So as our number of bolts are fixed, and with the help of your PCD or your BCD, which is nothing but your bolt circle diameter multiplied by pi, will give us the distance or the circumference of that PCD, and if we divide that with the number of bolts, we will be getting the actual spacing between the bolts. So we can have the higher size of the bolt used to satisfy the same area, or let's say we can have the smaller size of bolt with the larger number of bolts. Okay, so the same bolt area can be satisfied by any of the method. We can have larger bolt with smaller number, or smaller size of bolt and larger number. So it is like a kind of a tricky situation. Okay, so can we use only 2 bolts for any flange, or let's say only 4 bolts for any flange? There has to be some criteria to limit the maximum spacing between the bolts. Otherwise, there are chances at the midspan between the bolt cut, there is a chances of a leakage. So for that, in the code, they have given the maximum bolt spacing criteria. So that criteria says that BS max, that is the maximum bolt spacing, should not be more than 2a plus 60 upon m plus 0.5, whereas a is nothing but your bolt diameter and t is nothing but your flange thickness. So from this formula we will be getting the maximum bolt spacing, and the actual bolt spacing, that is nothing but your pi multiplied by the PCD divided by the number of bolts, will give us the BS. Okay, that is your actual bolt spacing. So that should always be lesser than the maximum bolt spacing. So that is one of the criteria for placing the bolts. Okay, now the final bolt load. Now the final bolt load for the operating condition, that is W, is nothing but W is equal to WM1. Okay, but in case of gasket sitting condition, the required bolt area was only AM, but we have selected more number of bolts. So the actual or the available bolt area is more than the required bolt area. So to take care of that, actual gasket sitting condition, W is equal to AM plus AB by 2 multiplied by the allowable stress of the bolt at the ambient condition. So by these two formulas, we will be getting the final bolt load for both the condition. Okay. But if you observe over here, AM plus AB by 2 is nothing but the average area. So for required bolt, we should have use only AM, and for available bolt, we should be using AB. But AB multiplied by SA will give us a very high value of W, and we may not be tightening the bolt to the full of its strength. Okay, so for critical application where lethal service is present, full bolt load should be considered, that is W is equal to SA multiplied by AB, and hence we will be designing the flange for the full strength of the bolts. Okay, so this condition basically is mostly used in the kind oil and gas application, where your full bolt loads needs to be considered for the flange design, because even a smaller leakage can cause a very big problem. Okay, so you may be knowing it very well that PVLET is also having an option, okay, like a checkbox, whether it's to be designed for the full bolt load or not. Okay, so those options are very well available in the software. So now, as we have done with the sizing of the bolt, okay, so number of bolts and then the bolt spacing. So now, what will be the next target? So the next target is to calculate the various moments. So for the operating condition, there will be three types of different moments which will be acting on any flange for the operating conditions. So these moments are MD, MT and MG. Now if we observe in the figure, okay, in the figure over here, there is a force capital HD, okay. This force is usually the force which is hydrostatic end force, which is applied at the ID of your flange. So here, as we know that moment is nothing but your force multiplied by the moment arm, that is the force multiplied by your perpendicular distance. So now all these forces will be considered to be acting with reference to the PCD, to be termed as the moment arm. Okay, so HD is nothing but the moment arises because of the force HD, where HD is hydrostatic end force acting at the ID of your flange, and hence the area across which the flange is applied is pi by 4 b square, whereas b is your flange diameter. So pi by 4 b square into p will give us HD, and the distance from this HD to PCD is termed as the moment arm. So if we observe, there is a capital R dimension over here in the figure, okay, and this HD. So in case of integral flange is applied at a distance G1 by 2 with reference to this dimension R. So what will be the total value? So the total value of HD is nothing but your R plus G1 by 2. Okay. So if you observe over here in this table 2-6, it is written as R plus G1 by 2, which is nothing but R plus 0.5 times of your G1. Okay. Then the another force which is acting in the annular space between the gasket load reaction and the ID of your flange. So this force is called as the H HT. Okay, so HT is nothing but the difference between the total hydrostatic end force acting on the area inside of the flange and acting between the gasket diameter G. Okay, so this is nothing but the force which is actually present on that annular area. So the actual value of that force will be the difference between the H, that is the total hydrostatic end force, which will be calculated as here pi by 4 G square multiplied by the pressure, and HD, which is nothing but here pi by 4 B square multiplied by the pressure. So this HT is a hypothetical force. So the moment arm is considered to be the average moment arm used for the hydrostatic end force as well as for the gasket load reaction. So the moment arm is considered to be acting for the HT, and the total distance from your PCD to the ID of your flange and the distance from the gasket load reaction to the PCD of the flange. So it is nothing but it is the average of both these two distances. Okay. So the distance between the ID and the PCD is nothing but here R plus G1. And the distance or the moment arm for the gasket load reaction Hg is nothing but Hg. So the average of these two is nothing but R plus G1 plus Hg divided by 2. So this is, you will find it in table 2-6. Okay. Now the next condition is Mg. So, so Mg is nothing but the component of the moment due to the force Hg. Okay. Now Hg is nothing but your gasket load, which is nothing but the distance between the total bolt load during the operating condition minus the total hydrostatic end force. So this is W minus H. Okay. So this Hg multiplied by the moment arm. Here the moment arm is nothing but the actual radial distance between your PCD and the gasket load reaction, which is C minus G divided by 2. So this is what you will find it in table 2-6. So Hg is C minus G divided by 2. Okay. So this is the moment arm used to calculate the moment arises because of your capital force Hg. So now the addition of these three moments will give us the overall moment for your operating condition. Okay. So let's talk about for the gasket seating condition. So now we have already calculated the bolt load W, that we have to multiply with the moment arm, which is the distance between your radial distance between the PCD and the gasket load reaction, which is nothing but your C minus G by 2. So in this way, what we have done is we have calculated the overall moment. Okay. So now again there is one more criteria before directly going to the stresses. Okay. So that is there is one more spacing which is important from the stress point of view. So it is called as the bolt space correction factor. So this is the correction factor used as a multiplier when the distance between the bolt, that is the actual spacing between the bolt, exceeds 2a plus t. Okay. Whereas a is your bolt diameter. Okay. And your t is your flange thickness. So if the actual bolt spacing is more than 2a plus t, then necessarily it has to be less than the maximum bolt spacing, that is 2a plus t upon m plus 0.5. So even though it is less than maximum spacing, but it should not also void your criteria of 2a plus t. So if it is more than 2a plus t, then we have to calculate a bolt space correction factor, which will be always having a value more than 1, and it is used as a multiplier which will be multiplying to your overall moment for both of your condition, for your operating condition as well as for your gasket seating condition. Okay. Now we'll come to our final aim to calculate the various stresses. So as in case of integral flanges, there is the hub present in the flange. So in that hub, there are two types of stresses developed. So one is your longitudinal hub stress and the other is your radial stress. Okay. And the last one is your tangential stress. Okay, so which will be going to be present in your flange. So this is the direction of the longitudinal hub stress which will be applied on the hub. It also depends upon your hub dimension. So these longitudinal hub stress are developed in your flange. So if you observe the formula over here, it depends upon m0, that is the overall moment, divided by some factor where b is your flange diameter, which is nothing but your ID of your flange, and G1 is your small end hub thickness. Then remaining L and F are the factors which depend upon the various hub dimensions like your G0, G1 and your hub length H. So from this, we will be calculating the longitudinal hub stress. Now radial stress, if you observe the formula for radial, again the moment divided by all these factors which are nothing but your geometrical factors. Whereas T is your flange thickness, B is your flange diameter, L, T, E are the factors which will depend upon the geometry of your flange. Okay. And the final stresses are nothing but your tangential stresses. So if you observe the formula again, it is ym0 upon T square B minus Z into SR. Whereas M0 is nothing but your overall moment, T is your flange thickness, B is your flange ID, Y and Z are the factors which depends upon the flange geometry, and SR is your radial stress. So in case of your tangential flange stress, some portion are already covered in your radial flange stress. Okay, so we are just going to, we only have to subtract that stress to calculate the tangential flange stress. Okay, so now as we have calculated the stresses, does the flange design is over? No, we have to compare the stresses with your final allowable stresses. Okay. So now for integral type of the flange, if you observe the PV Elite report, they have used the allowable stresses as guided by the code as 1.5 times of SF for the longitudinal hub stress, and for radial and tangential the value is equal to your allowable stress value what we have taken from your section 2 part D. Okay. Then these are the various graph which will depend upon the various geometrical properties of your flange, like your ratio of your ID to the OD of your flange, which will be called as the ratio of A by B, which governs your factor K. Then various hub dimension ratios like your G1, G0, then your hub length H divided by H0. So all these things depends upon the various type of your geometrical properties. Okay. Then the last step is we will come now to the allowable stress for the flanges. Now for the longitudinal hub stress, okay, if the basic material used for the flange design is a cast iron, then as we know the cast iron is having very minimum ductile property. Okay, so for that purpose it is limited to only SF. So SF is your allowable stress of your flange material at your design condition or your ambient condition. So when we say design or the ambient means all these stresses have to be calculated for the operating condition, and we have one moment, and for gasket sitting condition we'll be having the another moment. So for both these conditions we have to calculate all these stresses, and then we have to compare with your allowable stresses. Okay. So for operating condition, the allowable stress of that material will be at your design temperature, and for gasket sitting condition, the allowable stress will be at your ambient condition. So that's why SF is defined as the allowable flange stress at design or the ambient temperature as applicable. Okay. Now another thing is apart from cast iron, if the other materials are there, then the allowable stress for your longitudinal hub stress is the value used as 50% over the value we are getting from the ASME section 2 part D, table 1A or 1B, as applicable for your flange material. So as we are designing the integral flange, so here the shell is also contributing to the flange strength, but the weakest of the two will govern the flange design, and hence here the formula lies as the smaller of 1.5 times of SF or 1.5 times of SN, where SN is nothing but the allowable stress of that vessel or the pipe wall or your nozzle wall. Okay. Then when we are using the integral type of flanges, so there are two configuration. One will be your figure 7, what we have seen over there, which was where there were no butt joint, and all optional type of flanges what we have designed as an integral type of flanges. So as we know the construction of that flange or the type of welding, it is having a bevel along with the groove weld, okay, or a groove along with the fillet kind of a construction. And the typical integral type of a flange is where there will be butt weld, okay. So butt weld will always be having a higher strength as compared to your fillet weld, and hence that advantage code has given when the construction is having a butt weld. And because of that, if we observe, the allowable stress has increased to, over here, if you see over here, it is 2.5 times for that shell or the nozzle, okay. Now for the radial stress, the allowable stress is equal to SF only. For tangential stress also, the allowable stress is SF only. So does the flange design is over? We have calculated the stresses, we have compared those levels, and then we have made sure that all these stresses are below your allowable stresses. So does the flange design is over? So no. Still we have to calculate the combined stresses, that is the average stresses, means the ratio or the average of the radial stress and the longitudinal half stress should also be lesser than the allowable stress SH. So SH plus SR by 2 should be always lesser than or equal to SF. So if the flange needs to be safe, okay. And the other condition is the average, that is the longitudinal half stress, and the tangential also should be lesser than the SF, okay. So these are the various type of stresses which we calculated in terms of the integral type of flanges, okay. So now if we design the flange as a loose ring type of a flange, so there are only tangential stresses which are going to come into your flange. So there will be no hub, or even if the hub is there, it will not behave like an integral part. So these type of flanges will have no longitudinal hub stress, no radial stress, okay, and only tangential stress which will be coming into the picture, okay. And the allowable stress for the tangential stress is equal to SF only, okay. So in short, this covers the flange design calculation for the allowable stresses. But whether only based on allowable stress or based upon the developed stresses, if we have calculated the flange thickness, whether it will solve the purpose, or whether the leakage will be under the permissible value, okay. So the answer is no, okay. So if you see over here, the flanges that have been designed based on the allowable stress limits alone may not be sufficiently rigid to control the leakage. So code is saying that even if we have calculated the stresses and those are below your allowable stress, but still there are chances that the flange can still may fail. So what is the reason of that, and how the code has given the remedy over that? So what they are saying is the rigidity factor uh, provided in table 2-14. Okay. So if you see over here, this is the table 2-14, where they have been it has been proven through the extensive user experience for a wide variety of joint design and their service conditions. So what they are saying is, based upon the various experiences observed by so many customers, they have developed one index which is called as the rigidity index, and we have to make sure that that index should be always less than 1. It also depends upon the moment and the other geometrical parameters, and also the Young's modulus of that material. So it should always be less than or equal to 1. Okay. So what it is written over here now, the use of the rigidity index does not guarantee, though the code is also saying that even if we are doing this, does not mean that the flange is 100% leak proof. Okay. So the use of rigidity index does not guarantee a leakage rate within the established limits, but it should be considered as one of the factor for the joint design. Uh, Earlier, this was not an integral part of the flange design in the older versions of the code, but later on they have made it mandatory. So now it is compulsory for all the flanges to have rigidity index as checked. Okay. Another point over here, there is one alternative, or some, what you can say, there is an exception given where it is allowed to waive off the requirements of the flange rigidity. So if we have any past experience of the flanges which are still in the service, and those are designed without rigidity index, and they are serving like for a longer period of time, so we can have that advantage provided none of the following conditions are violated. So what are those conditions? So what the code is saying is successful service experience may be used as an alternative to the flange rigidity rules for the fluid services that are non-lethal, non-flammable without exceeding the following conditions. So the main condition is that the flange or the process requirement is non-lethal and non-flammable. So if those are lethal and flammable, then it is mandatory to consider the flange rigidity. And if you see over here, there is a limit on the temperature. Is the temperature should be within the limit of minus 29 degrees centigrade to plus 186 degrees centigrade, and the design pressure should also not be more than 150 psi. So can we say now that the flange design is completed? So yes, we can say that unless and until there are some external load which are going to come on your flanges, then we can conclude that for the stresses and rigidity index, what we have checked, okay, so the flange design is completed. But if there are some external loading or the forces or the moment which are coming because of the piping, so that also needs to be considered during the time of flange design. Okay. So this was all about the theory of the overview kind of related to the flange design. Now we are going to see how to optimize the flange design. Okay. So as we all know that your flange design is an iterative method where we have to assume first the parameters according to which we have to calculate the stresses and then your rigidity index. And also if the stresses are lesser than your allowable stress and your rigidity index is lesser than 1, then whatever parameters we have selected, those are whether those are approved or that whether that flange is safe or not, that we are going to check. So first we have to assume the flange parameter and then we have to start with the flange design. So how to optimize the flange? What would be the procedure or what are the steps that which we can design the flange at a first glance, or you can say in one go? Okay. So when we are designing any flanges, what are the fixed parameters with us? So let's say we are designing the weld neck flange. So we have the shell to which this line is supposed to be welded. Okay, so the flange thickness at the lower end of its hub, that is G0. Basically, we usually start the design assuming it is which is similar to that of your shell thickness. So let's say we have the value of G0 and the ID of the flange. So these are the two parameters which are fixed. Okay. So we always have to start from these fixed parameters. Okay. So as a flange design is an iterative method, we also have to assume the flange thickness. Okay. And then we have to make sure that whatever the flange thickness we have selected, whether it is safe or not. Fine. So let's start. So let's say we are designing the weld neck type of a flange. Okay. So first in PVLID we have to select the flange type. Okay. Then the first fixed parameter what we have is the inside diameter. Okay. So we have to enter the flange ID which is exactly equal to your shell ID. Then the next thing is your flange thickness. So as I said, it is an iterative method. So first we have to assume the flange thickness. So we have assumed the flange thickness over here as 40 mm. Okay. Then your other fixed parameter is nothing but your small end hub thickness, that is G0, which is similar to that of your shell thickness. Okay. So these are the fixed parameters from where we have to start any flange design. So apart from the thickness, where your thickness is, we have to assume. Okay. So now as we have finalized, your ID is there, G0 is there. So now the next parameter one should address is after G0, we have to assume a value of G1. That is nothing but your large end hub thickness. So we know for a weld neck type of a flange, there is a taper to the hub as 1:3 slope. Okay. So we have to maintain that. So means whatever difference between the large end hub thickness and the small end hub thickness, that will be multiplied by 3 that will be your hub length. Okay, so to have this, either we have to assume the hub length or we have to assume the G1, that is your large end hub thickness. Okay, so let's say your 8 mm is our G0. So if I assume G1, that is the thickness at the large end of the hub, as 9 mm, so the distance is only 1 mm, and in that case your hub length would be 1:3, means 1 multiplied by 3, so it will be 3 mm. So it will satisfy the code requirement. Okay, but there is one more code requirement, which is nothing but your hub length should not be lesser than your 1.5 times of G0. Means what? Since we have assumed G0 as 8 mm, okay, so 8 mm is there, so your hub length at least should be equal to 12 mm. So this 12 mm divided by 3 will give us 4. So we can have large end hub thickness as 12 mm and the hub length as overall difference of 12 mm, that is here 4 mm. Okay, so there are two criteria. One is 1:3 slope, and the other is the hub length h should be greater than or equal to 1.5 times of your G0. Okay. So now whether the 12 mm hub length what we have calculated, will that be okay? Okay. So mostly what happens if we take this as 12 mm. So mostly well-neck type of flanges are used where radiography is preferred. Okay, so it is difficult to have such a small pair or a space to conduct the radiography. So that is one criteria. Another criteria is the butt welding angle of 70 degree. That should also be met. Okay. So another thing is if there is any repair comes, then we have to address that repair also. So the access in that 12 mm will be very minimum. Okay. So it is difficult to address all these things. So considering all these things into the mind, at least 25 to 30 mm of your hub length that we have to assume. So the minimum hub length should be at least 25 to 30 mm. So now let's say 30 mm we have assumed. So 30 divided by 3, that will become 10, correct? So that 10 mm is the height above G0. So what G1 I have to assume is as at least 18 mm. If it is more than that, then naturally your hub length will become more. Okay, so let's say it is 20 mm. So 20 minus 8 becomes 12 multiplied by 3. So it becomes 36. So your hub length becomes 36. That is acceptable by code because it is meeting all the requirements, your radiography requirements, your access point of view, and also practical point of view. So obviously it will be safe. Okay. So now in this example, in this case, what we have added as we have added 9 mm with your G0 value, so it becomes 27 mm to satisfy the minimum code requirement, correct? So now we have finalized the hub length and we have finalized the G1. Okay. Now the next is we have to choose the bolt diameter and the bolt material. Then we have to choose the size of the bolt as well. So depending upon the size of the bolt, there are distances from hub to bolt and bolt to edge, which is there in TEMA table D5. Okay, so you can see over here we have selected M20 bolt. Okay, so your hub to bolt distance is nothing but your RS distance, which is 31.75 for this bolt, and your bolt to edge distance is nothing but your E value, which is 23.81. So again, if we go back to PV Elite, they have mentioned it over here. If you see, okay, so PCD is nothing but your ID plus 2 times of G1, which is 17 plus 2 times of your hub to bolt distance. Okay, so that we have got from the TEMA table D5. So it becomes total becomes 1097.5. So we have taken the value as 1098. Clear? And the other distance is, since we have finalized the PCD and then we have to finalize the OD. So from PCD to OD, the edge distance we have to maintain. So if you observe over here, the 23.81 at the bottom, so it is also taken from TEMA only. So we don't have to go to TEMA every time. So PVLIT is showing those distances at the bottom. Okay. So now we have reached to the PCD, correct? Then whatever number of bolts we have selected, okay, Then now we have to enter the Mn Y factor value. Okay. Then the next is we have to finalize the gasket OD as your PCD. Okay. Minus the bolt hole minus your 2 mm clearance. Okay. That's how we should be having the gasket ODS fixed. Okay. And then we have to consider a 15 to 20 mm as your gasket thickness, your width of the gasket, and from that we have to calculate the gasket ID. Okay. So why this 15 mm we have taken over here? So that will come to know in the later stage. Okay. So now we have finalized your gasket ID as well as your OD. So based on this, your face ID and OD will also be going to be finalized. So your face ID is equal to your flange ID and your face OD is equal to your gasket OD. So now we have to check whether the bolt area is sufficient or not. Okay. So here the bolt area is insufficient. So now there will be two options, whether I can increase the number of bolts or you can increase the bolt area by changing the size of the bolt, correct? But if you increase the size of the bolt, the available bolt area will increase. But by changing the bolt size, your hub to bolt and your bolt to edge distance will also going to change. So because of that, your PCD and OD of the flange will going to change again. Okay. So instead of changing all this dimensions, what I am just doing is I am just trying to increase the number of bolts and trying to match the requirements. Okay. So let's say we have started increasing the number of bolts, and when it becomes 44, it has observed that the bolt area is passes and the required thickness for that flange is nothing but 75.946. So I have to change this thickness to 75.946. Okay. So what will be whatever thickness? So at low pressure, where your gasket parameters or the gasket seating stresses are having the higher values and the bolt load coming for the seating of the gaskets are more, there we should design the flange in such a way that your gasket should be placed as near to the PCD as it can be at your lower pressure. Okay, but for the higher pressure, your gasket factors or your gasket is not controlling the design. So there you can have gasket placed anywhere. So it doesn't have much of the difference. Okay. So now over here in this case the pressure was less and the gasket was 3N69. That is nothing but a spiral wound gasket. So the required thickness is 75.946, which is controlled by your gasket and not by your operating parameters. Okay. So here we have to increase the thickness to the next available thickness, which is nothing but your 78 mm. So the thickness has been increased. Okay. Now over here we have placed the gasket as near to the PCD. So if we place the gasket ID which is equal to your shell ID, then we have the same width of the gasket. And what effect it will going to be have on your design? So let's say if your gasket is defined from the flange ID, okay. So if your gasket ID is equal to your flange ID, and we have the same width of the gasket, and as gasket is controlling the design, if you observe over here the thickness has become to 92. Earlier it was 76. So just by changing the place of the gasket, your thickness can be optimized in a very great way. So as a designer we always have to see that which condition is governing. So whether it is your gasket seating or whether it is your operating condition, correct? Okay. So we have increased the thickness over here. So now we come to the gasket. So how to define the gasket width? So now from table 2-4 in ASME section 8 division 1, for a composite type of a gasket, they have given some recommendation. Again, it is just a recommendation. It is not a mandatory thing. Okay. So what they are saying is till 900 mm, at least 25 mm gasket you have to use. Above 900 mm and between 1500, 32 mm. and above 1500 38 mm. So if you use such a high width of the gasket, your gasket load will be having very high and your thickness of the flange will always be very high. So is there any other alternative provided in any other code or from other standard? So if you see over here, in TEMA, they have given for this peripheral kind of a gasket for RCB class, they have given us 9.5 mm and 12.7 mm at least you should be giving. So that's why usually for spiral wound type of a gasket, 13 mm is the width what we are usually selecting. Okay. Also in division 2, they have given for a composite or a sheet gasket and for the spiral wound gasket. So if you observe, the maximum width of the gasket even for the composite is 19 mm only, and for the spiral wound also it is maximum as 16 mm against 38 mm and 32 mm what we have seen in division 1. So we know very well division 2 is the more evolved version of your division 1. So here also they have reduced, and basically division 2 is used for the higher pressure, correct, above 3000 psi. So for this reason we are choosing it as between 13 to 15 mm as the gasket width. Okay. Then another condition over here, whenever there are different design condition, always your flange is designed in a pair because it is to be tightened with some another flange. So no individual flange can be used. So if it is not to be bolted with the other flange, so usually whatever flanges we are designing, those are to be designed in a pair. So in a practical example, there are certain conditions where both the flanges will not going to have the same operating or the design condition. So let's say in case of a heat exchanger, it is having a shell side and tube side. So in most of the cases, here shell side and tube side pressure and temperature both are different. So you will be getting the different thicknesses for the flanges. But the bolts what you are going to use, those will be common to both. So let's say for a one flange, 1000 kg is the bolt load required. For another flange, 2000 kg is the bolt load required. So if I apply 2000 kg of bolt load, the weaker flange will leak. Correct? So that's the reason why whenever you are designing such a flange pair where the design conditions are different, there you have to transfer the bolt load from one flange to the another, whichever will be governing. Okay, so let's say tube side flange is having the higher bolt load. So in PVL also at the time of designing at the lower portion there is a tab where it is asking for the loads. You must have seen the loads partition gasket, and obviously you guys are using it. So there we have to select that option and then we have to enter those values of WM1, WM2 and W for the higher flange. So that for the lower flange at the time of designing, the software will compare this value with the actual value, and if these values are more, the software will consider those values. So monitoring and the bonnet, its right hand side of your shell will always going to have a flange which is having the higher diameter than your other part of a flange. Okay, so if you observe over here, the pressure temperature are same but the dimensions are different for both the flanges. So as the flange design is also depend upon the various ratios like your factor K, which depends upon the ratio of your ID and OD of your flange, which is your A and B, whereas your B is different, that is your flange ID. So as your flange ID is different, the loads coming because of this ID is also going to be changed. So here also we have to transfer the higher loads to the lower flange. Okay. Then the last is, now again, if there are any external load for which the flange needs to be designed, then if there is any axial force, that also we have to convert to pressure, and that pressure we have to add it into the design pressure. This is only when the axial force is in the actually outward direction, which is nothing but your tensile in nature, means it is supporting the pressure. So the primary function of that pressure is to separate the flange. And if let's say the weight of the equipment or your some axial force which is trying to push the flange down, so it is actually acting in a reverse direction to the pressure. Okay, so there we don't have to consider that effect. Okay, but if it is pulling in nature and it is supporting to the pressure, then it may help pressure to open the flange. So in that case, we have to convert that axial force into equivalent pressure, and then we have to add that equivalent pressure into the design pressure while designing the flange. And the moment out of these three moments, the torsional moment will not have any effect, but the other two moment, which is your circumferential and your longitudinal moment, out of these two, the maximum value of the moment we have to choose. Okay, so from that equivalent pressure we have to calculate. But if your axial force which is acting in the downward direction, so it is not actually supporting the pressure, it is in the reverse direction, but we don't have to take that advantage that it is trying to close the flange. So as per division 2, what they are saying over here is, according to division 2 equation, this axial force will have to be considered if it is tensile, that is pulling force. In other case, the value should be taken as 0. So they have defined it as Fa, the value of the external tensile net axial force. So your compressive net section forces are to be neglected for that case, and hence Fa should be taken as equal to 0. Okay. So if it is compressive means it is in the downward direction and you don't have to consider it. Okay. So this completes the flash design. I hope, I think I have taken a lot of time, but it was a very huge topic. So I hope I have covered most of the points related to this topic. So we obviously we know that you guys are the better designers, but this was just a kind of a knowledge sharing session. So we thought of expressing our views. Okay. So I will not waste much of your time. I will just show you some key features of the PV Elite 2019. Okay. So let's start. So these are the few of the things which we are going to talk about: the productivity enhancements, the new code and code updates, analysis items, the output generation and reports, and then followed by the if you have any questions. Okay. So starting with our productivity enhancements. So one of the item over here is the automatic pad diameter calculation. So whenever you are designing a nozzle and then you think about that you need to go for the reinforcing pad. So you know that there is a little bit trial and error involved. Okay. So you type in the new pad diameter and then you see what it happens until you get something works right for you. So what they have done in 2019 is, when you click on the radio button next to the icon that has a pad, okay, so you can see it over here. So what PVL it will do is, it will automatically do the iteration for you, and it will come up with a pad diameter that works for you, okay, which will meet your code requirements. Fine. So this was the change which has been done in this version. Then another new option right here is to specifying the nozzle projection. So what people have asked for the dimension H0, if you see over here, but you know that it will be very easy to calculate, but sometimes it can be a little inconvenient if you know what the projection HF shown over here in the sketch is. So in this version, you can just type in the HF value, and when you press OK, earlier this was not there. You need to press only the projected value. Based on the projected value, the software was calculating the outside projection. Okay. But if now in this version, if you enter the H0 value, the outside projection that the software really wants will be calculated for you. Okay. Then the another enhancement is, it may be of some help to you, is nothing but your enhanced flange design. So what they have done in this version is, when you select the flange type that you want, okay, whatever type you want, and then from here you specify the M and Y factor value. Okay, and then you press the design button which is there over here in the bottom. And then what PVL it will do is, it will quickly rough out a flange design. And based on that, you can very well optimize it, okay, if you want to. So, but this is really a very quick way of roughing out the body flash design. So just by entering the M and Y value and just clicking on the design button, the software will just give you some rough out of your flange design. It will design the flange for you, okay, and then you can very well optimize it. And the next is the another enhancement over here was to make the insulation transparent. So now you don't have to use those few clicks to turn off the visibility, which was quite confusing during the time when the insulation was, because of the insulation you are not able to see few of the components. Okay, so now this insulation will be hidden. Then in this new version, the help system has been updated compared to the earlier one. You can see very well there is a huge change in the help guide. Then the next item is the embedded learning or the predictive reasoning and analytics. So what it is doing is PVL it will learn from one or more users at a time. Okay, this will reduce some part of your work. Like for example, if you always use the same wind and seismic code and things like that, like it will be nice when you set up a new model. Those things will be automatically populated, and that's what it does over here. Okay, so as you are working on the different model, PVL it will record and save the data, and then it analyzes when you start a new model. So currently they have done this for few of the items. However, they will expand it in the near future. But obviously, as you can see over here, you always have a choice whether to use this feature or whether you are not interested to use this feature. So you can very well click it over here. Okay. So here are few of the things, for example, which will get generated for you. So you know when you start in the model, the things like your joint efficiency, your head factor, and various other things like your split pad checkbox over here for the section at division 1, then your nozzle material, then your flange material. So when you start a brand new nozzle, you may see it, you will be getting all these informations automatically filled for you. Okay. So that is what the software is doing it now. So it will record all the data if you have done once, and if you want the software to use this in any another project, so then it will take all the informations automatically for you. Okay. Then another feature is like as you guys be knowing that PVL it is used in worldwide. So just this was a request from the other countries that they want to use commas instead of the decimal places. Okay, so that also has been incorporated. So if you don't want uh, commas, earlier we were using it the decimals. Okay, so that also is there in the settings where we can check it. So use commas instead of decimal in your numbers, so that will be reflected in your report. Okay, then next is your new code and code updates. So obviously this year's it was not an ASME code update here. So that will going to be the next year. So PVL it 2020 will be having an ASME code 2019 edition. So but there are some other codes they have updated which PVL it addresses. So here are a few of them. So IBC 2018 seismic code has been added. Then Japan's KHK seismic code level 1 and 2 has been added. The Mexican seismic code to 2015 edition has been added. Also, PD 5500 2018 plus Addenda 1 has been incorporated. And further to that, they have updated their fatigue analysis, and also type 2 jacket analysis has been added for PD 5500. There were some updates to EN 13445. The testing groups 1 to 4 have been added. And also type 1 and type 2 jackets have been added for EN 13445. Okay. Then coming to the analysis items. So you may have seen in the earlier version where they have added this feature of generation of minimum safe operating temperature curves. Was earlier it was for vessels, now they have added for the heat exchangers. So now we can generate the MSOT curve for both the shell side and the tube side of the heat exchanger. So they have updated PVLIT to generate a pressure temperature curve, which is known as your MSOT curve, and then it will display in your output processor application, so that your analysis can process a temperature and your pressure plot to check for the unsafe conditions. Okay, so this has been added. Then another item right here is you may be knowing very well about this code case 291. A lot of interpretations were coming on this. This has been added in the earlier version also. So what it is exactly? So you know when you have forces and movements on a nozzle connection. So when you are trying to determine with if the flange is okay or not, then there are some equations that go through this. And obviously this was there in the last version, but due to the user feedback, what they have done is they have gone something little bit further with the detailed calculation. Earlier we were only getting this check report, so we were not able to identify what the software is doing in the back end, but now you will be getting the complete detailed report for this. Okay, and also the for the PVP method, it will be named as code case 2901. So this will be included with all your formulas. Okay. Then another thing is to do with the full bolt load for heat exchanger tube sheets. So you must be knowing that your part UHX does not address things like the full bolt load requirement, then your bolt space correction and things like that. That you might have to find it in appendix 2. So as the geometry of the tube sheet is something different than your typical flange. However, to meet the need of the users, they have allowed, of course, as an option that you can use in case if your customer requires to do so. Okay. Then the next thing over here was the calculation of the MAWP for the pressure testing. So for heat exchangers, as they operate at different pressure and temperature on each side, so you really can't just calculate the MAWP for the whole thing. But as you know, PVLIT does calculate the MAWP, but it is for a specific set of design condition, which can then be used to determine the hydro test pressure. So the concern was perhaps earlier it was not including the thermal, it was including the thermal cases as well. Okay, so uh, now they have given you a checkbox where it will allow you to very specifically control it. So if you don't want the thermal cases to be added in your MAWP for the test condition, then you can check this box as well. So it will be basically based on your pressure cases only. Okay, so this has been added. Then the next is they have extended the service type and the radiography requirement for the heat exchangers. So we have separated the shell side and the channel side for those items. So this you will be seeing it in your heat exchanger tab. So these new options will be there. Then these are the few of those list of the analysis items and content, like your longitudinal stress consideration for your MDMT calculation. Then we have API 660 nozzle load tab available for heat exchangers now. Okay, so this API 660 nozzle load table will be there now. Then the number of new saddle database dimensions have been added. Along with that, the Taiwanese structural steel database also have been added. Then your factor and unfactored loads are now separated and printed in the output. What exactly it is, like if you're using a seismic code like ASC7, where there is a sort of a conversion between the load factor design and the allowable stress design. So, but because of some of our engineering companies, they may only want to see only one set of load or the other. So, like to have them separated. So, what maybe they can be more efficient in their concrete design and something like that. So that is the reason now we have separated both the loads, the factor load and the unfactored load will be separated in the output. Then few other things right here, like the material of construction in the vessel summary. So now we have got some tables that will sort out all the different materials that you have used. Then your local stress summary, that also we have got it now. Then a new metric bolt table has been added. So this was also a request from some of our user. So with this, they have also added the user-defined bolt table where you can customize your bolt table as well. Okay. Earlier, this option was not there. Another work what they have done with it is related to WRC 107 and 297 on the output side. Here the PM plus PL plus Q. If you have sustained loads only. Okay. So earlier it was taking more than the 3 times of your part material allowable. So now it has been revised that your allowable will be taken with your 3 times the part material allowable. So it has been revised over here in this version. Then they have also done something that you will find in your section 8 division 2, that this allowable can also be computed between your two temperatures. So that also has been taken care of. Then they have also looked into, like if you're in the creep range, there's also some consideration in the calculation of the allowable for the creep range temperatures. So that also has been taken care. Then another is the pollen research group FEA expansion joint solver has been updated. So the main part of the update was the calculation or the printing of the stresses at the stress classification line. So if you look at the TEMA, they show you where these points needs to be, where the stresses are to be reported as. So when you run an FE expansion joint calculation in PVLE 2019, you are going to see a lot more information now. So that solver has been updated up to quite some extent. Then, as we have discussed over here, there is a new report you will be getting it for the material of construction. Okay. Then similarly for the local stress analysis report. So if you got things like the nozzle with the loads or clips or whatever you have. So, but this is for all the codes. Okay. So you will be getting this report. Fine. Then the last is the output generation and reports. Okay. So here what they have done is the weight report has been revised. So now it will clearly show which column the element and detail weights are, how they are subdivided, and how we come up with all our numbers. You see over here. Earlier it was quite confusing that whether this load has come from where and this is of which loads. So people used to ask the justification for that. So now you can see how all of the numbers add up in this different column. So that we have been highlighted over here. Okay. Another thing they have done is regarding the vessel lifting. Okay. So vessel lifting operation over here. So obviously, depending on how things happen, if you have a column and you are bringing it out to the site, then things like the platforms. So are they installed before the column is lifted or after the column is lifted? So knowing such situation, so you have got few new checkbox over here that will allow you to actually tell the software when these things are added. Along with that, they have also added a new pull down selection for like which weight do you want to use for the lifting analysis. The value that comes out in the erected weight column or the empty weight column or the way the PVLit was doing it earlier. Okay. As I said earlier also, there are always you will be having an option whether to use it or whether you don't want to use it, whether you want to go with the what PVLit was earlier doing it. Okay. So you have the choice.